For your lesson today, we will be focusing on permutations and combinations. The objectives are that students will be able to apply the multiplication principle of counting to solve problems. Students will be able to identify permutations and combinations of various sets, and students will be able to utilize permutations and combinations to solve problems. So we're going to get into what permutations and combinations are. All right, but we're going to start out by focusing a little bit on that activator problem that we looked at. We're going to discuss that in a little more detail. And then in the instructional focus, what we're going to be doing is we're going to look at the multiplication principle, permutations, combinations, what they are, and what we call subsets of an n set. And we'll get into what that really means as the lesson continues. But let's take a quick look at your activator. We had 3 different circles of different colors, and what we asked you to do was to take these circles and tell me how many different ways could they be arranged in order. So if I were to label them with letters, the purple one being A, red being B, yellow being C, we could arrange them as, and if we look at this tree diagram on the bottom right, we could go A, B, C in that order. We could go A, C, B in the second order, etc. We could start with B. All right, we could go red, purple, yellow. Or we could go red, yellow, purple. So each of these is a different kind of path we could take. And if we look, we end up having, let me clear that off. We end up having 1, 2, 3, 4, 5, 6 distinct possibilities. All right. And in the lesson today, we're going to find out how we could come up with that result, that number 6, without having to go through and listing each possible way. And we're going to do this because it's going to help us with much more complex problems that deal with much larger numbers where we still need to determine the number of possible combinations, etc. So to start off, we have something that we call the multiplication principle of counting. All right. So some procedure has a sequence of stages, stage 1, stage 2, stage 3, all the way up to stage n. All right. Some predetermined number of stages where n represents that number. All right. And we know that stage 1 can occur in R1 number of ways. So it could be 2, 3, 4, 5, however many different possible ways it could occur. Stage 2 can occur in R2 ways, etc. Stage n can occur in whatever Rn ways is. Then the number of ways that the procedure can occur is the product. It's going to be R1 times R2 times R3 all the way to Rn. All right, if we think about our activator, we had 3 colors. The first color listed could be one out of any 3 colors, so it could exist 3 different possible ways. Once we have one set, we only have 2 colors to choose from, so it would be 3 times 2. The final stage, we're left with just 1, so it could only occur in one way. 3 times 2 times 1 equals 6. We could have come up with that number of 6 distinct possible ways by using this multiplication principle of counting. So let's look at another example. At the bottom of the screen, we see this Tennessee license plate, a Tennessee license plate, and it says shown here. I don't actually have the image here, but it consists of 3 letters of the alphabet followed by 3 numerical digits. So it could be like, A, B, C, 1, 2, 3. Something like that would be the license plate, right? It's 3 letters, 3 numbers. Find the number of different license plates that could be formed. All right, so for example, if there's no restriction on letters or digits that can be used, meaning it could be like A, 1, 1, 1, and then the second one, no letter or digit can be repeated. And there's going to be a big difference in our results. All right, the first way, where there's no restrictions, the first letter could occur 26 different letters. The second one could also be 26 different letters. The third one could be 26 times 26 times 26 times. There are 10 different number combinations, so times 10 times 10 times 10. And that would tell us the full combination. If you can't repeat, then you would be 26 times 25 times 24 times 10 times 9 times 8. And the reason why we have to reduce our numbers as we go in the second one is because we can't repeat, meaning our number of possible numbers to choose from is getting smaller every step of the way. All right, and if we actually multiply this out, right, we multiply 26 times 26 times 26 times 10 times 10 times 10, that gives us about 17.5 million different possible license plates. Now, if we don't allow for a repetition, it actually reduces it to about 11.2 million license plates, which is a big difference. If a state had this restriction where you couldn't use a letter multiple times, it would significantly impact the number of possible license plates. If they needed to somehow come up with a way to provide more because, say, they ran out of you know, license plates that have been issued and there are more cars or something like that, then they would not restrict it, and it would provide a significant boost in the number. So take that into account when you're using this multiplication principle, is whether or not we're allowed to replace or not replace the numbers as we go through the different steps. So when we use the multiplication principle of counting, we're counting the number of ways a set of n objects, which we call an n set, can be arranged in order. That's what we're doing. So each such ordering we call a permutation. All right, so when we had the three different colors, red, purple, yellow would be one of the permutations of that particular set. All right, the example that we just that we looked at with the colors, right? We said was we showed that it was 3 times 2 times 1, which is the same thing as what we call 3 factorial. Anything factorial is just that number times all the numbers behind it. And so based on that first warm-up problem, we could find that there are n factorial permutations of an n set. So if we have a set of 3 objects, there are 3 factorial permutations. If we had 10 objects, it's going to be 10 factorial, meaning 10 times 9 times 8 times 7 times 6, etc. All right, so if we look at this next example, where we're asked to count the number of different 9-letter words, all right, don't worry about whether or not they're in the dictionary, so different letter combinations, right? We have 9-letter words, and we're going to say how many different permutations of letters are there in each word. Well, since it's 9, we just said, the number of permutations in the set would just be 9 factorial. So we could just say, it's going to be 9 factorial for each of them. This is going to create an issue. All right, in the word dragonfly, all of the letters are unique. But in butterfly, we have 2 T's. In bumblebee, we have 1, 2 B's, 3 B's, and we have 3 E's. So all of a sudden, if an E is an E, regardless of which E we're referring to. This becomes a little bit difficult in determining permutations because, EE here, if I were to switch these 2 E's, we still have the exact same permutation of letters. So what do we do about that? So what we do, all right, is we have to remove all of the permutations that involve those duplicate letters. And the way in which we do that is we divide by, in butterfly, there are 2 letters, so we would divide by 2 factorial. In the third word, in bumblebee, we had 3 B's and 3 E's. So we divide by 3 factorial for the B's, and we divide by 3 factorial for the E's. So we would go from dragonfly, where we had 362,000 permutations, to butterfly, where because of the 2 T's, we lose half. So we go down to 181,000. But with bumblebee, because we had to divide by 3 factorial twice, we drop all the way down to 10,000 distinguishable permutations. All right? And so we can see that those duplicates matter. And the way in which we handle them is by dividing out the combinations that we determine for those duplicate letters. So remember, how many permutations are there of the 2 T's? Well, 2 factorial, right? How many of the 3 B's? 3 factorial. So that's what we're dividing out because it takes care of all of those duplicate entries. So based on that example, we learn how many distinguishable permutations there are. Is going to follow this formula here, where n represents the total number of distinguishable objects, so n factorial, divided by the number, all right, of objects of each kind. So for example, in bumblebee, all right, in bumblebee, we had n factorial, so that was 9 factorial, the number of letters, divided by how many B's are there? Well, there are 3, so that's going to be 3 factorial. How many U's are there? That's just 1 factorial, which is fine. We can put that in, 1 factorial, which is just 1. So that means if there's anything that's just a single letter, you don't need to include it because dividing by 1 doesn't have any effect. There's only 1 M. We already counted the B's. There's 1 L, and then there are 3 E's. So that's why it's 9 factorial over 3 factorial times 3 factorial. and that gives us the distinguishable permutations. So now we have something called the permutation counting formula, which is a little bit different. All right, the number of permutations of n objects taken r at a time. All right, and we'll get into what this means in just a second. Is denoted NPR like this, and it's given by that n factorial divided by n minus r factorial, where r is a number that's greater than 0 and less than or equal to n. All right, if r is greater than n, then it's going to just be 0 because you can't choose more objects than exist in this. So an easy way to think about what this permutation counting formula is doing, it's basically saying, let's say we have n objects and we want to know, all right, so say we did 6 permutations of 4, right? This essentially is telling me, I want to know how many different ways could I take 6 objects and choose 4 of them and arrange 4 distinct objects, meaning we wouldn't use all 6. This is why if r is ever greater than n, you have too many. You can't, if it was 6p7, right, you can't pick 7 out of 6. It just doesn't work. That's why that would give you 0. And we'll take a look at what exactly this is referring to right here. So the number of permutations of n objects taken r at a time is denoted that n permutation r, NPR, and it's given by this formula. So now we want to go ahead and see what this means. So let's look at A. All right, if I had 6 letters, A, B, C, D, E, F, and I wanted to know how many different ways or how many different permutations do I have of 4 of them. I could have A, B, C, D. I could have A, B, C, E. A, B, C, F, etc., etc., etc. How many different permutations of these letters could we come up with? This is going to be 6 factorial divided by 6 minus 4 factorial, or 6 factorial divided by 2 factorial, which is just going to be 6 times 5 times 4 times 3 times 2 times 1 all over 2 times 1. Well, the 2's and 1's are all gone. It's just 6 times 5 is 30, times 4 is 120, times 3 is 360. So that would give me 360. And that's how we would go about doing that particular problem. There are 360 different permutations of letters that I could make where I have a pool of 6 to choose from, and I'm only selecting 4. Another way we could have looked at this is to just use the fundamental counting principle straight up from the very beginning. For the first slot, I have 6 possible items. For the second one, there would be 5. For the third, there would be 4. For the fourth, there would be 3. 6 times 5 times 4 times 3, guess what? That gives me the same 360. And that gives us the same result. That's where that formula really comes from is, we just take that initial principle. How many do we have to choose from? 6. On the next one, because I've used one of them, I now have 5, then 4, then 3, etc. So if we look at the solutions for all of them, that's how we could find, for example, B. 11 times 10 times 9 gives me 990. For the third one, N, choose 3. Well, I'm not really sure what I would do in that situation, but we can just use that principle. So we just say we have N objects, so the first time it's N times N minus 1 times N minus 2. That's just like saying 10 times 9 times 8, or 11 times 10 times 9, depending on what n is. If n is 100, it would be 100 times 99 times 98, because we just have the 3 to fill, and that would be our answer. And we would have to assume that n has to be greater than or equal to 3. So how might we apply permutations? So say we have 16 different actors who are answering a casting call to try out for roles as dwarves in a production of Snow White and the Seven Dwarfs. How many different ways could the director cast the 7 roles? So we have 16 people, all right, and we're trying to find out how many permutations exist where we select 7. This is just going to be 16 factorial divided by 16 minus 7 factorial, or 16 factorial divided by 9 factorial, which is the same thing as just saying 16 times 15 times 14 times 13 times 12 times 11 times 10. All right? When we multiply all that out, we find that there are over 57 million ways that the director could cast those roles. You might not have thought that, 16 different actors, 7 roles. You probably wouldn't have guessed that the number of possible permutations would be that large, but it is, which is just a really interesting thing that we can see using permutations. So we're going to end this lesson here at permutations, okay? When we discussed the different objectives for today's lessons, we talked about combinations as well. In our next lesson, we'll focus on combinations, and we'll take a look at this subsets of an n set. But for today, you guys learned about the multiplication principle and permutations. All right, and you should be able to determine the number of permutations in a set, and you should be able to answer questions like that Seven-Dwarf question, right? We should be able to apply the different formulas that we learned with regard to permutations and the multiplication principle of counting to be able to solve some different types of problems.